Welcome back. We've been discussing about partial molar properties, and so I'll just do a quick recap of what we have learned in the last lecture. We defined a term, a generic property, partial molar property, which is nothing but the partial derivative of K. K could be energy, enthalpy, internal energy, enthalpy, and other extensive variable with respect to Ni's. Okay. So, this is nothing but an intensive property, and we said, well, Ki bar is going to be Ki, that is a molar property of a component I for the pure case when the Xi goes to 1. And the examples could be partial molar property for the volume case, partial molar enthalpy, and so forth. Then we also talked about Euler integration, that the K which we talked about in here is generic property. If you use a similar approach as we have done in the past for the Gibbs free energy, we should be able to show that K is nothing but summation Ni Ki bar. And using this and using the concept of Euler integration, one can show that Ni di Ki bar is equal to 0. That is the Gibbs-Duhem relation at a constant temperature and pressure, and this is something which we can use it for example for relating some variables, as we have done that for binary mixtures, to those which we know. In other word, we can relate let us say the partial molar volume for component B to the derivative of the partial molar volume for component A as an integral of that with respect to dxa. Okay. If you have information of this, then essentially we will be able to obtain V B bar. Then we also talked about the property change of mixing, that means how much change in a given variable or extensive variable K, okay, when you mix few components, and this is something which we can generalize as K minus summation Ni Ki. Okay, and then we divided by n and we obtained that delta K mix is nothing but summation Xi Ki bar minus small ki. And we took a case of a mixture at a steady state where we said, well, if you mix component 1 to m at a constant temperature and pressure, then the final mixture is at a temperature and pressure, then delta H of this mixing is nothing but the Q here. So, enthalpy of mixing is the amount of Q required to produce a mixture at temperature and pressure from pure component at the same temperature and pressure in a continuous flow process. Now, so we will continue from here and we will take a case to get a feeling of partial molar property. We will start with molar volume, partial molar volume. Okay. So, let us consider the case of water and ethanol. Okay, and what we are interested is to understand what happens to the contribution of the water when it is mixed. Let us say you have container which is maintained at a constant temperature and pressure. Okay. And there is a flow here which allows the water to get in, and this is a volume V and number of water, and this is for let us say ethanol. Okay. So, this is the case that initially this is a straight and this is a water flow, and one can find out the volume, molar volume of water for such a case. For the pure case is nothing but we know that here is coming at 80 milliliter per mole. Okay. Now, we will take a case where basically, so this is the initial state, and now we will take a case where we have added a small amount of mole to the volume. Okay. So, let me just again draw it here. Okay. Now, in this case, of course, there is a small change in the volume delta V, and what has happened that we have added small amount of W small delta n has been added here. Again, remember this molar volume still remains the same, and now the total volume is now changed to V1 plus delta V. So, this was V1, okay, and then NW2 is NW1 plus delta NW, and number of moles of ethanol still remains the same. Okay. So, what would be the V of partial molar volume for water in such a case? Okay. So, this will be your del V by del NW, right? That is the definition at a constant temperature and pressure F and E, and this particular experiment which we just did entirely realize that we have maintained the temperature here at T and P, keeping the number of moles for ethanol fixed, and added a small differential amount of water, and that means I can approximate this as, okay. So, if you do this exercise in experiment, you would be able to find that this is nothing but 16.9 milliliter per mole. Okay. So, what it tells you that the contribution, okay, of water to the mixture is less, right, than that of pure species. Okay, so this is what it tells you, that that contribution finally is less, which also tells you that water ethanol apparently interaction leads to closer packing than exclusive okay. So, it tells you that water ethanol interaction leads to closer packing than exclusively water interactions. So, this is precisely due to the hydrogen bonding in this case. Okay. So, we talked about delta H here, right. If you look at it here, we talked about delta H. Let us say now we again go back to this water ethanol case and find out from experiment using the same exercise which we have done, because delta H is nothing but Q. Now, you can do you can vary the composition of the water and ethanol in such a way that you should be able to measure the Q here. So, if you can measure the Q, essentially you can find out the delta H mixture as a function of the composition of, let us say, ethanol in a given mixture, and then you can plot it. Okay. So, let me show you one of the plot for different temperature. Okay. So, this is your 0 and this is your delta H mix, and this is joules per mole, and this is a composition X, where we are saying this is essentially composition of X of ethanol. Okay. So, again this is a water, so this is a water ethanol now. So, if I can measure the Q for different temperatures and compositions, you should be able to see the variation of this behavior of delta H mix with respect to temperature. So, this is the case where we are getting something like this. Okay. So, this is your 300, 320, 340, and then I can go up to get. So, this is approximate, if you okay, just for the schematic representation here. Okay. So, this kind of behavior where the composition variation can also change the sign of the delta H is also observed in such kind of mixtures. So, what does this sign represent here? For the case of negative, that is less than 0, we know that it is going to be exothermic, okay, which means that you need to remove the heat from your chamber or container where this mixing is happening in order to maintain the temperature. Okay. That means heat must be removed to maintain temperature. Similarly, you can, for the case of greater than 0, you have endothermic, which means temperature must, which means heat must be added in order to maintain the temperature. Okay. So, let us do one example here. Okay. So, this is a question related to again water and ethanol. So, it is to calculate the temperature rise when 0.8 moles per second of water is added to 0.2 moles per second of pure ethanol. Okay. In an adiabatic, so basically the Q is 0 in such case, adiabatic continuous flow process. Okay, so the other thing is that the input conditions are both the input streams are at 300 Kelvin and 1 atmosphere. Okay. So, how do you proceed for such a case? The diagram here, if you have such a diagram available to you, you know precisely what is delta H mix for x is equal to 0.2 mole fraction. Okay, so mole fraction is 0.2 for ethanol. So, we can find out here. So, this will be somewhere, some value is there at 300 Kelvin, which essentially here somewhere, and this value turns out to be minus 750 joules per mole. Okay. So, let us say this is given to us. So, delta H mix, okay, at x is equal to 0.2, T is equal to 300 Kelvin is minus 7 and of course 1 atmosphere. Okay. Now, this tells you that this is exothermic, right. So, this is exothermic. So, temperature will rise because the mixing is done in adiabatic continuous fashion. Now, in order to find out the temperature rise, we need heat capacities. Okay. So, we can think of this way that so essentially the final temperature, let me try to simplify this. So, you can assume that there are two components, right. So, one is water and other one is ethanol. So, we can take this let us say pure component, let us say 1 at temperature T 0, which is 300, to temperature pure 1 at T final. Okay. And similarly, you can have the second component, which you can also go to another one pure 2 T final, and the mixing can occur at a constant temperature. So, this mixing can occur at a constant temperature, right. So, in that case essentially what we can find out is your delta T is, let us say, change from here, right. So, this is a change in the temperature from taking to 0 to final. So, what I can do is I can actually consider based on the heat capacity, because this is nothing but a sensible heat or energy which is taken from this point to this point. Now, we have the information of mole fraction. So, this will be C1 Cp1 delta T plus 1 minus x Cp delta T, and then this total energy plus whatever the energy related to mixing, this must be 0 because of the adiabatic conditions. So, with this you can find out delta T as nothing but minus delta H mix by x Cp1 plus 1 minus x Cp2. Okay. Now, you can think of this as one approach. The other approach is, of course, you can mix it at T0, okay, and then take the complete mixture to that. There also you will be doing the same exercise. So, this could be also at delta H mix at T0, which is basically the 300. Now, with this information and with this delta H mix information available for us, we rather use the second part where we say that, well, we are mixing it at T0 and taking it each of the component to the final state or final temperature. So, with this you should be able to add this part here, and then you get this information of Cp1 and Cp2 from the NIST Web of Science or from various different textbook tables. This information is given to us, and the problem here, which is 112.4 for ethanol, okay, and this is 75.3 joules per mole for the case of water. So, using this with using the information of delta H mix, we should be able to find delta T, which turns out to be around 2 Kelvin. Okay. So, that is a problem one which I wanted to solve. Now, let us move, and so now let us try to further explore this concept and look into the partial molar enthalpies from total enthalpy. In other words, we will do another problem to understand this concept, and in this case what is given to us is not in a diagrammatic form delta H mix, but in some expression. Analytical forms of delta H mix is available to us, and then subsequently we will like to find out what is a partial molar enthalpies in this case. Okay. So, again this is example. Okay. So, let us say that molar enthalpy of a binary mixture at a constant temperature and pressure is given by delta H mix C x1 x2. So, this is the expression given to us, where C is basically nothing but a constant, not a function of temperature, pressure and composition. Okay. Now, the question is that we need to find out the or obtain the partial molar enthalpies of the two components, okay, and verify the Euler theorem for homogeneous function, which is H is equal to summation Ni Hi bar. So, this is nothing but the Euler theorem for homogeneous function. Okay, so this is a problem given to us. Let us start with the definition of a delta H mix first, because that is the expression given for us. Delta H mix here is nothing but H minus summation Ni Hi at the same temperature and pressure. Okay. Now, I can find from here H is N1, because there are two components here, N1 H1 plus N2 H2. H is nothing but the small h is nothing but the pure molar enthalpy of the pure component plus delta H mix. Okay. So, delta H mix, so this in fact this what is given to us is this underscore, which means is a molar delta H mix. So, I should be able to write now as N times delta H mix. Okay. So, this I should remove it for clarity. Now, this information is given to us, right. So, this is something which we can plug in this value here. This is nothing but RTC x1 and x2, right. Now, I can now use x1 as n1 by n1 plus n2. Similarly, this is n2 by n1 plus n2, and this is nothing but n1 plus n2, right. So, I have this information of H. Now, from this information or this expression, I should be able to calculate partial molar enthalpies for component 1 and partial molar enthalpy for component 2. So, in order to get that, let me first take the differentiation. That is how I am going to write it. This will become H1 bar, and that will be differentiation of N1. Okay, whatever I am going to put it here. So, that is going to be N1 S2 plus N2 S2 plus. Now, if you expand it, this becomes N1 N2 divided by N1 N2 N1 plus N2 square, but N1 and N1 plus N2 also is a numerator. So, what I get here is CRT N1 and N2 divided by N1 plus N2. Okay. So, if you do this partial derivatives, I should be able to get the following expression: H1 plus CRT N1 plus N2 square N2 N1 plus N2 minus N1 N2. Okay. So, this further can be simplified as CRT N2 by N1 N2 square by N1 N plus N2 square, and this is nothing but x2 square. So, therefore, H1 bar is H1 plus CRT x2 square. Similarly, you can show that H2 bar is nothing but H2 plus CRT x1 square. Okay. Now, given these two, we should be able to now show the Euler relation of this. So, if you plug in this, what do you get? N1 H1 bar plus N2 H2 bar. So, now we can check the Euler's expression. Okay. So, N1 H1 bar plus, okay, this is nothing but N1 plus N2, right. Whatever this relation we wrote here, this was H1 plus CRT x2 square, this is H2 plus CRT x1 square. So, this can be written as N1 H1 plus N2 H2 plus CRT is common, and this will become N1 x2 square plus N2 x1 square. So, this is the relation we got. Now, if we further can simplify this, so this is the same term plus CRT. If you simplify, you get N1 N2, N1 plus N2 square, N1 plus N2, and then you have this denominator N1 plus N2 square. So, because x2 is of course N2 square by N1 plus N2 square. Now, with this relation, I can cancel out this. So, what remains now is that N1 H1 bar plus N2 H2 bar is nothing but N1 H1 plus N2H2 plus CRT N1 N2 divided by N. Okay. This is indeed the case if you look at it how we got it. This was the case, right. So, this was N1H2 N1H1 plus N2H2 plus N delta H mix. So, can I write it then again? So, I can write this as, I can multiply this, right, and then I can write this as N square N1 N2, and now this is nothing but x1 x2, and this term finally is nothing but the same expression which we wrote, that this is N1 H1 plus N2 H2 plus N times delta H mix bar, okay, the molar part. So, indeed we obtain the same expression, and that is what how we verified it as well, right. So, this is something which we have not done. Now, let me take it another problem, and I think perhaps that will further elaborate the use of this partial molar properties in terms of solving it through analytical means. So, this is again an example. Okay. So, in this case what we have is the partial molar volume of component 2 in a binary mixture at T and P is given by the following expression. So, is V2 bar is equal to A plus B x1 cube, right. So, what is being asked is to relate the constant A. So, find A in terms of molar volume of pure component and obtain our expression for the partial molar volume of component A1 and volume of mixing. Okay. So, you have to find out partial molar component of volume 1 and volume of mixing. Okay. So, so looking at this expression, you can clearly tell one aspect that when x1 is 0, that means when it is a pure component, then V2 bar is nothing but A. So, let me start with this thing. For pure 2, x1 is 0, which essentially means V2 bar is A, and this must be same as small V2, which is a molar volume. Okay. So, A is nothing but, so that is something which we can clearly come out, we can write down this from the expression. Now, we need to find out the partial molar volume of component 1. So, we will start with the Gibbs-Duhem relation, because this is the one which relates both the partial molar properties with the composition. So, for the binary one, we can binary component, we can write this as okay. So, this now we have the expression already, okay, and this I can now use this expression of V2 in order to obtain it, but let me just first rewrite this thing as del V1 by del x1, temperature pressure, this is minus x2 by x1, del V2 by del x1, okay, and here I can plug in the expression. So, I get minus 1 minus x1, and this I can write as okay. Okay. So, I have now the expression. If you take this the derivative of x1, then essentially this is going to be 3 bx1 square, and I can write this as 3bx finally 3bx1 because this will cancel 1x1 and hence I got this expression. Okay. So, this is the expression I have. I can integrate now v1 as 3b x1 square minus x1 dx1 or b x1 cube minus 3 x1 square by 2 plus c, right. So, this is the expression of v1 bar. Now, if we put x1 is equal to 1, this would mean v1 bar should be equal to small v1, and if you put x1 here, this also means that this is nothing but minus b by 2 plus c, because if you put x1 here, this will become minus b by 2 plus c. This means c is nothing but v1 plus b by 2. So, we got an expression of the v1 bar. Now, v1 bar can be written as now v1 plus b x1 cube minus 3 x1 square by 2 plus half. Okay. So, we got an expression of v1 bar, and we have also v2 bar, which we know this expression, and here of course we got a we replaced by small v2, that is a molar property. So, now we can write everything now in terms of b when it comes to delta V mix. So, we need to find out the final term is delta V mix, which is nothing but summation xi Vi bar minus small vi, right. So, in this case a binary one, binary component, or in this case is a binary mixture. So, it is x1 v1 minus v1 plus x2 v2 minus v2. Okay. So, if you plug in this expression which we got here for the v1 bar, and we know for the v2 expression, this will turn out to be b x1 x2 1 plus x2 by 2. Okay. So, this was a very simple mathematical exercise which we have used in order to obtain the relevant information, and the key element was that we use the limiting conditions and gives to him relations in order to find the unknown information. So, that will be the end of today's class, and we will continue this exercise in the next class as well. Okay, so, I will see you in the next class.